So the diode is a basic semiconducting device. It's one of the building blocks of solid-state technology. Transistors, you use those in IED. ICs, you use those. Microprocessors, they're all based on diode theory. And diode applications covered include rectifiers. Rectifier means taking AC, converting it to DC. Clampers, we'll do some clamp and clipping coming up. Voltage regulation, we're going to do that with the Zener diodes. And LEDs, we're going to use in a variety of labs. These are all semiconductive NMP type material, okay? Now, how we develop these is that if we look at a germanium atom on the left and the silicon atom on the right, silicon atom on the right has 14 protons, and it's considered to be neutral. It is considered to be a semiconductor, meaning that's halfway between conductor and an insulator, so having 4 valence electrons. Versus a germanium, you look, each has 4 shells, so 4 electrons in its outer shell. Germanium having 32 protons versus silicon having 14, but still, you know, semiconductive material. So, and when they line up, these outer shells connect, they share, this is called a covalent bond. These outer shells share these electrons, and they create this lattice silicon crystal structure. So it appears full with 8 electrons. Now, what happens is when I introduce an N-type material, and hopefully you remember what we call an N-type material when we're producing, it's called the process of producing the N-type material, which means it is primarily negative, is doping. We are actually doping. Think of Lance Armstrong. Every time I say doping, I think of Lance Armstrong. Now, what we're doing is we're introducing an atom that has an excess electron. As we can see here in red, we have an excess electron. So if I have an excess electron, I have 1 more electron than I do protons, so it is inherently a more negative type material. So that electron is free to sort of roam throughout the lattice structure. And it isn't until I apply a force on that, then all of a sudden, when I apply a force that is the same as that, in other words, a negatively charged electron, that electron is going to be compelled to move. And of course, it would move to another area where there is an opening for it, so into a p-type material. So, for example, this is arsenic. Arsenic has 5 valence electrons. So we have this 1 extra free electron that is free to move. Conduction through N-type material. So that's a block symbol for N-type material. So looking at this, if I was to look at this, I would say we're talking about current flowing from negative to positive, because that's, you know, we talk about electron flow theory versus conventional theory. So we'd have electrons moving from left to right. And I discussed last week the difference between, hole theory and electron flow theory. I'm not going to get back into that, even though there is a slide. I'm not going to get into that. We already chatted about that. It really doesn't matter, so long as your fundamental understanding is how this happens to flow. So let's take a look at p-type material. So when you think of p-type material, I want you to think of more positive type material. So again, we're going to dope it, but this time we're going to dope it with something called gallium. So we have silicon atoms, 4 valence electrons, then we gallium. But notice the gallium only has 3 valence electrons. So what happens is it leaves this spot here where essentially we have a hole being created as a result of doping the material. And if we have a hole created, and if we think back to our other slide where we had a N-type material, we had an excess electron. So now if we create an excess charge on one side and an N material and a lack of charge on the other, then now we have somewhere for that electron to go from the N-type material into the p-type material. So again, in p-type material, electrons still flow from negative to positive. However, the Hall flow is equal and opposite to that of the electron, because when the electron leaves its space, it leaves behind, you got it, a hole. Okay. This is the block symbol for a diode. The schematic is in black below it. So one way of remembering, because this was one of the common issues that students had yesterday, was, like if you take a look at this, I say this, if 2 ways. So you can think of this as being like this here, this line, this vertical line here. If you were to remove that vertical line and flip it to the side, it would look like a negative. So that's the cathode side, typically denoted with a K. This is the anode side. So we usually identify the cathode side. So on your diode, it's going to have a stripe. So that would be the cathode side. Another way of remembering this is if you were spray painting cabinets, this looks like, if you're over here and you're spray painting, that kind of looks like your spray paint. It's fanning out and spray painting. So we're spraying electrons onto the anode. So anode lead and cathode lead. Now, one thing you're going to have to do tomorrow is you're going to have to determine what your barrier potential is. And the barrier potential is a function of the depletion region. So let's talk about the barrier potential and the depletion region. So again, this should be a review from last year, but I know that it's been a while. And if you have any questions, please text them in. So here we have an N and P-type material. Now, when you take N and P-type material and you put them together, you've got all these positively charged semiconductive material and a negatively charged semiconductor material. The negatively charged has these electrons that are free to move. And you have the P-type material, which has an excess hole in it. So what ends up happening is you get this, it's called diffusion, where the electrons will move over to the positive P-type material, filling those holes, leaving behind holes in the N-type material. So essentially what's happened is it almost flips polarity. You get this barrier potential of voltage. And what you have to do is you have to overcome that value of barrier before this will start to conduct. Now, why is this important? Well, this is important to understand because every diode, whether it be a rectifying diode or a light emitting diode, has a barrier potential. And that is a value that you must deduct from your calculations to get a correct answer when you're calculating a rectified DC wave. So the materials exchange carriers at the junction, and a thin area called the depletion region is zoned. Depletion zone is formed. So in forward bias, you can see on the left in the blue, I have a positive charge that goes to the positive on the battery, and then I've got the negative that the N-type material that is connected to the negative material here. And as you can see, in forward bias, we're going to get electrons that are repelled from the battery and pushed over into the holes in the anode and then over to the positive side. So because like charges repel, these electrons are going to move, and they're going to move to the holes on the P-type material. Now, in reverse bias, notice that the yellow N-type material, those electrons are attracted to the positive on the battery because I've got this connected wrong. And the positive holes are attracted to the negative potential on the battery, creating this area at the junction zone, that PN junction. That the PN junction is where the P-type material meets the N-type material. We end up creating what's called a depletion zone, meaning it is depleted of any potential charge. So there's no ability for that to conduct. Now, of course, we can make it conduct in reverse bias, but in doing so, we destroy the diode. So looking at a typical diode characteristic curve for conduction, we see that once we get past the 0.7 volts for silicon, you're going to measure your own tomorrow. And it says on the lab, use 0.7 for your value of barrier voltage. But yeah, I'm not going to have you do that. Do not use that. I am requiring you to measure your own diode and put it down and replace that value where it says use 0.7, scratch that out and put in what your barrier potential is. I'm going to show you how to read that in a minute. Now, in forward bias, once we exceed the barrier potential, we start to get conduction. Now, I can get this to conduct in the reverse direction, but look, it takes a lot of pressure to get it to conduct in the reverse direction. And all of a sudden, boom, when I apply that voltage in the reverse bias to the diode, it will start to conduct, but it starts to conduct, that is reverse breakdown voltage, and we call that avalanche current, as it looks like an avalanche. Now, when you're looking at diode leads,